Okay, we'll talk about chapters 29 and 35. Chapter 29 is about thermochemistry. This is information you should have learned back in Gen Chem 1 that we need to apply onto our chapter 35, which deals with chemical thermodynamics. Let's cover some concepts first. First one, let's define thermochemistry. Thermochemistry is the study of the energy effects that accompany chemical reactions. So why do chemical reactions occur? What is the driving force of a reaction? Well, the answer to these questions deals with stability. Reactions want to get to a lower energy state to be more stable. For a reaction to take place spontaneously, the products of the reaction must be more stable, meaning at lower energy, than the starting reactants. When we say something is spontaneous, it means that the reaction is going to occur on its own. Okay, it will go from reactants to products. Eventually, over time, maybe seconds, maybe minutes, maybe months, but the reaction will eventually go from reactants to products. Basically, the reaction is in control of that happening. Contrary to that is something called non-spontaneous, which means it will never happen by itself. Okay, it will never change from reactants to products by itself. The only way that that reaction is going to occur is it has some outside energy, some outside source to help that reaction to go. We can draw this with an energy diagram. So I have my, I could have my reactants go into products. In this case, you can see that my energy associated with my reactants is higher than my energy associated with my products. Since my reactants are at a higher energy, they're less stable and more reactive. For this reactants to go to products, I have to lose energy. So in the process of losing energy, okay, this would be a spontaneous reaction because it's in control. The reaction can go from reactants to products by a process of releasing energy. So it has all the energy it needs. In fact, it's got too much. It releases it, and it goes from reactants to products. That's a spontaneous reaction. A non-spontaneous reaction would be something like this, where I have reactants going to products. My reactants here are at a lower energy, okay, therefore they're more stable and less reactive. The driving force of reaction is it wants to get stable, it wants to get to a lower state of energy. So these reactants are already at that point. So for it to go from a lower energy to a high energy state, it's going to have to absorb energy, okay, from some source to make it happen. That's what we refer to as a non-spontaneous reaction. Basically, for these reactants to get to products, it's going to have to absorb energy from somewhere else to make that happen, which hence is a non-spontaneous reaction. Another way of looking at this, to give you a definition of spontaneous versus non-spontaneous, let's say I had a hill, and I had a bowling ball on the side of the hill, and I had my finger on that bowling ball holding it there. What do I have to do to get that bowling ball to roll down the hill? Exactly, just lift my finger and that ball will go down the hill. That's an example of a spontaneous reaction. It has all the energy associated with it due to that potential energy of its height to get it to go down the hill. Now let's take that same hill, and now let's take the bowling ball and put it on the bottom of the hill, and I put my same finger on top of that bowling ball, and my goal is to get that bowling ball on top of the hill. If I lift my finger, what's going to happen? The ball's not going to move. Can that bowling ball get to the top of the hill by itself? The answer is no. Okay. But can that bowling ball get to the top of the hill? Yes, from some outside force. Okay, I could pick it up and carry it up there. I could kick it up there. The wind could blow it. There's many different ways it can get there from external forces. Okay, so the bowling ball on top of the hill is what we're referring to as a spontaneous reaction, while that on the bottom of the hill is a non-spontaneous reaction. It can occur, it just can't occur by itself. It's going to need some external force to help it happen. In chemical reactions, heat is often transferred from the system or reaction to the surroundings or vice versa. So let's define these terms. First, the system. The system is the substance or mixture of substances under study in which a change occurs. So basically, it's the reaction that we analyze. Okay, that reaction that we're studying is the system. The surroundings are everything in the vicinity of that thermodynamic system. So the surroundings is everything else. Okay, so if the system is the reaction, the surroundings would be the flask, the room, the solvent in that flask. Those are all the surroundings. So we can draw that in a picture formation if we wanted. So we're basically saying the system or the reaction is what we're studying, and then everything else is the surroundings, the flask, the solvent, the room, whatever. Those are all the surroundings. And typically what we're trying to measure in this reaction, this system, is the internal energy of the system, which we can represent as delta U. So typically we're measuring that internal energy of that system. Now, one thing to keep in mind is that everything going into and out of the system is going to be determined by some signs, okay? And to keep in mind that when we're going into the system, okay, if I'm going into the system, we're talking about a positive value. If it comes out of the system, we're using a negative. That plus and minus is just a representation of going into or out of the system. It has nothing to do with plus and minus, okay? It's just telling me a reference of going into or out of the system. And the majority of what we're looking at is in terms of the eyes of the system, okay? So positive means into the system, negative means out of the system. Heat flow is defined as the energy that flows into or out of the system. We follow heat flow by watching the differences in temperature between the system and the surroundings. Often, what we tend to do is follow the surroundings temperature, the solvent. We can measure that typically, so usually we measure the solvent, but you got to realize that the opposite has happened to the system. So if that system is absorbing heat from the surroundings, then the temperature of the surroundings must be decreasing. Okay, so if I'm doing an experiment and I'm basically measuring the surroundings, okay, I know that if the surroundings temperature is going down, because I'm watching the thermometer and see that the surroundings, the solvent is going down in temperature, then I know that reaction, that system temperature has to be going up. Okay, so we represent that change in the surroundings temperature with a negative, and that change in that temperature of the system going up as a positive. What we're typically doing is watching that transfer of heat, okay, as into or out of the system. Heat flow, or heat of the reaction, is denoted by the symbol Q, and is the amount of heat required to return the system to a given temperature at the completion of reaction. Now we have some terms we use to state that the flow is going into or out of the system. For an endothermic reaction, the sign of Q is positive. Heat is absorbed by the system from the surroundings. The surroundings are supplying that heat, okay, that system is absorbing. So basically in the diagram, okay, I have my surroundings, I have my system. We have heat that is being absorbed from the surroundings to the system. So what's happening is my temperature of my surroundings then is going down because it's giving that heat to the system, and my temperature of my system is going up, which the net effect would mean that the total energy of my internal energy of the system is going up. So as my surroundings temperature is going, as my temperature of my system is going up, the temperature of my surroundings is going down, okay? This surroundings is supplying that heat to the system. So then that means my total energy, internal energy of the system is going up as well. Now, going back to my potential energy diagrams, which one are we talking about here? That would be the case where I'm going from reactants to products, from a lower energy of reactants to a higher energy of products. For that to occur, it has to absorb heat, okay, from some source, and then the reactants will go absorb that heat and then form the products. This is an endothermic reaction where I have heat being absorbed by the system from the surroundings. Now, if we're only talking about heat, okay, that endothermic reaction tends to be non-spontaneous. Now, there are other factors that can sway whether the whole reaction is going to be non-spontaneous or spontaneous. But if we're just looking at heat, okay, just looking at heat, endothermic reactions tend to be non-spontaneous. That doesn't mean that just because it's endothermic that it's a non-spontaneous reaction. As I said, there's other factors that are involved to make sure to decide whether the whole reaction is spontaneous or non-spontaneous. And we're going to talk about those factors in chapter 35. For an exothermic reaction, the sign of Q is negative because heat is evolved or released by the system to the surroundings. So we're looking at that. We're looking at a case of my heat is going out from the system to the surroundings. So what's happening there is my temperature of my system is going down, okay, which means my surroundings is absorbing that heat, so my temperature is increasing for the surroundings, which means since heat is leaving the system to the surroundings, that my total internal energy of the system is going down. Now, the potential energy diagram that this represents would be the case for the spontaneous reaction where my reactants are going from a higher energy level to a lower energy level. So then I'm releasing energy to the surroundings from the system. This is referred to as an exothermic process. And we said that this is a spontaneous reaction if I'm just talking about heat. Once again, it's got to look at the overall picture. Okay, exothermic is a spontaneous reaction if we're talking about just the heat component, but there's other factors that may be involved that may take that exothermic reaction and make it a non-spontaneous reaction as well. As discussed, we will discuss this later in chapter 35. The heat absorbed or evolved by a reaction depends on the conditions under which it occurs. Example, pressure is one condition to be concerned with. Usually a reaction takes place in an open vessel and therefore under a constant pressure of atmosphere. Heat of this type of reaction is denoted QP, where Q stands for heat, and that subscript P indicates that we're at constant pressure. This heat at constant pressure is named enthalpy. Okay, is given the symbol H. So basically, enthalpy is the heat flow at constant pressure. So when we use enthalpy, okay, we're talking about the heat flow at constant pressure. Okay, so when we're talking about enthalpy, that capital H, we're dealing with heat flow at constant pressure. Enthalpy is an extensive property of a substance that can be used to obtain the heat absorbed or evolved in a chemical reaction at constant pressure. So when we talk about enthalpy, we're talking about heat either absorbed or evolved in a chemical reaction at constant pressure. Now, another important word in this definition here is extensive. Okay, what does it mean that enthalpy is an extensive property? An extensive property depends on the quantity of substance there. If it's an extensive property, it means it depends on the quantity of substance there. Examples. The mass of something depends how much there is, how much mass is going to be there. The volume of something depends on how much is there, determine the volume. Okay. Another extensive property is enthalpy. It depends on the amount of substance there. If I have a ton of wood compared to 100 grams of wood, which one's going to generate more heat? Well, since I have more substance in my ton of wood compared to that 100 grams of wood, obviously my ton of wood is going to generate more heat, hence an extensive property. Okay, so enthalpy, dealing with heat, is an extensive property. Depends on the amount of substance there as to how much heat is going to be generated. Contrary to if we say something, talk about intensive property. Intensive property does not depend on the amount of substance there. What are examples of that? Well, if I had 5 grams of water or 100 grams of water, it's still going to boil at the same temperature. Okay, the boiling point is an intensive property. It doesn't matter how much substance I have, it's still going to have the same boiling point. Color. Doesn't matter if I got 5 grams or 100 grams, it's still going to be the same color. Okay, those are both examples of intensive properties. Enthalpy is a state function, which means a property of a system that depends only on its present state and is independent of any previous history of the system. Okay, since it's a state function, all I care about is where it starts and where it ends. I don't care what happens in between. Okay, state functions are or usually things that have a delta function. Okay, so delta x. So when I'm talking a state function, okay, say delta x, x being anything, could be temperature, enthalpy, or whatever. It's going to be your final values minus your initial values. Okay, your change basically. That delta means change. okay, change in that X value. Now, we can do that in different things. Say, for example, let's do it in temperature. I could have something that starts off at 50 degrees C, and it may change temperature and go up to 100 degrees C, then go down to a negative 10 degrees C, then end up at 80 degrees C. Okay? What we're talking about with this state function is all I care about is where it starts and where it ends. I do not care about where it went in between. Okay? All I care about is where it was and where it ended up and the difference between it. So in this particular example, I'm looking at my change in temperature. I'm talking about my final temperature minus my initial temperature. I'm talking about 80 degrees C minus 50 degrees C, which gives me 30 degrees C. That's my delta T. Now the other thing to realize is that's 30 degrees C relative to where it was before. Okay, this is a relative thing, not an absolute. I'm not at 30 degrees C. I'm 30 degrees C higher than I was before. Remember, I was at 50 degrees C, now I'm at 80, so I'm 30 degrees higher than I was before. If I had a negative sign, then it would mean I'm 30 degrees below where I was before. So basically that result is a relative value compared to where I was before, not absolute. The reaction enthalpy of a reaction at a given temperature and pressure can be solved using delta H, okay, since it's a state function, which would mean my enthalpy of my final minus my enthalpy of my initial. However, we don't talk about final and initial when we're dealing with reactions. Typically, we have some reactants going to some products. So in our terminology, initials then will be my reactants, enthalpy, and my final will be my products. So typically when we write delta H, what we're talking about is our enthalpy of our products minus our enthalpy of our reactants. Basically what we're looking for is the net effect or change in heat in a reaction. Once again, we're talking about a relative scale, not an absolute. What we want to do is determine the change in that enthalpy between my reactants, how much enthalpy it has, to how much enthalpy is associated with the products. What is that change between those values? As we already stated, the reaction enthalpy is equal to the heat of reaction at constant pressure. This represents the entire change in internal energy minus any expansion work done by the system. Therefore, we can define enthalpy in internal work by the following equation, which is referred to as your first law of thermodynamics. In any process, the total change in energy of the system is equal to the sum of the heat absorbed and the work done by the system. In other words, delta U is equal to Q subscript B, P, meaning constant pressure heat plus work. Now, we've already redefined our heat at constant pressure to delta H. Okay, so first law of thermodynamics at the present moment for us is delta U is equal to delta H plus W, where W is work. Changes in energy manifest themselves as exchanges of energy between the system and the surroundings. These exchanges of energy are two kinds, heat and work. We must account for both. Heat is energy that moves into or out of the system because of a temperature difference between the system and surroundings. As we discussed, we measure that change in heat between our reactants and products. Work is the energy exchange that results when a force F moves an object through a distance d. In other words, work is equal to force times distance. Well, this is the physics definition, so we need to talk about it in terms of chemistry. So what we tend to do in chemistry is talk about some reaction. We can do it in terms of expansion of the volume or compressing of the volume, and there's some pressure associated with that. So basically what we tend to do in chemical systems, work is defined as a change in volume at a given pressure. In other words, work is equal to a negative P delta V. Okay? Now, this negative sign is there because we need to have that work in the eyes of the system. Okay, if that system is doing work, we need that work to be negative work to show that the internal energy of the system is going down. If that work is positive work, in other words, the surroundings doing work on the system, then that means energy is going into the system. We need that to be positive. Okay, that way the internal energy of the system is going positive. So let's talk about that negative sign and show why it has to be like that. That way we can do it in the eyes of the system. All right, let's talk about in terms of expansion work first. Okay, if I'm talking about expansion work, then what we're saying is that my final volume is larger than my initial volume. Okay, which means that if I calculate delta V, I have my final minus my initial. My final is larger, a larger value than my initial, which means then I'm going to have a positive delta V. If I plug that into my equation, I have a negative P delta V, then my overall a negative time a positive will give me a negative work, which basically means that the system is doing work. Well, if you're expanding something or if you're pushing on something, okay, if you push on something, then you're doing work, right? If I'm pushing out on something, I'm doing work, okay? So my internal energy is going down. My energy is going down. So we need this work to be a negative value because the system is doing work when we do an expansion, okay? The volume's getting larger, so the system's pushing out and pushing that volume up. So therefore, we're talking about it, the system doing work. Therefore, the total internal energy of the system is going down. Let's talk about contraction. In that case, you're talking about a final volume being less than your initial volume. So if you talk about your change in volume, you got your final minus your initial. Your initial volume is larger. Therefore, you have a negative delta V. Okay, if I plug in a negative delta V, now I have this negative time a negative, which now gives me a positive, right? Which means that there's an increase in internal energy in the system. Okay, so if I have positive work, that means that the surrounding is doing work on the system. Well, if you're contracting something, let's say I had a ball and I'm pushing on that ball, I'm putting energy into that ball. I'm pushing energy inside that ball, increasing that pressure in that ball by pushing on the sides. So the surroundings is doing work on the system, okay? Hence, I'm increasing energy into the system, so I want that value to be positive. So this is why we have this negative sign in front of P delta V to keep it in the eyes of the system. That if the system's doing work, okay, I got negative work. If the surroundings doing work on the system, I have positive work. Which gets us back to the first law of thermodynamics and putting it in a more useful format, which is delta U is equal to delta H. And instead of having work, now we're going to put negative P delta V, okay, which is our first law of thermodynamics. All right, for homework, okay, homework 44 deals with using this equation, the first law of thermodynamics, and basically it's just plugging and chugging into the equation. Now, there's some mistakes that can happen, so you need to make sure you realize that. Number one, units, okay, the typical units on delta H is in kilojoules or joules, while pressure tends to be atmospheres, and volume tends to be in liters. Well, I can't subtract kilojoules and atmosphere liters. Okay, they have to be the same units. Okay, I subtract kilojoules from kilojoules or liter atmospheres from liter atmospheres. Okay, so you're going to have to convert liter atmospheres into kilojoules, okay, or joules before you do your subtraction. That's where one mistake can happen. Okay, now typically in the homework I give you that conversion factor for you can do it. Okay. The other thing is you got to realize that the signs, okay, if we say that the amount of heat is absorbed, okay, then you got to put a positive value when you plug it into your equation. If we say the amount of heat is released or evolved, then you got to put a negative sign into your equation. Okay, these signs you're going to have to put in based on the words that are given to you with that energy. Same thing with work. If we say the system is doing work on the surroundings, then you got to talk about negative work. If you talk about the surroundings doing work on the system, Then you're going to talk about positive work. Okay, so you got to make sure that you put in the right value, a plus W or a minus W, when you plug those values into your calculations. This is where sometimes in practice you get an answer and then you go to homework and you get the wrong answer, because what you didn't realize is you got to read every word. One word changes it. If I may have absorbed in the practice one, but in the homework I have release, then you have to change the sign. So make sure you're reading the problems carefully when you plug it into this. Otherwise, it's a very straightforward plug and chug type problem.